Okay, so from Friday or Thursday, whenever you did your lab, we graphed force versus distance. And you guys were such good little graphers that you got something really cute like this. And eventually, that looked like that the force was proportional to 1 over d squared. You might have squared it and then realized it was an inverse relationship, or made it an inverse and then had to square it, or you may have just jumped to 1 over d squared immediately because you figured it out. But once we graphed force versus 1 over d squared, we got a nice straight line. And that was good, because then it shows us that we are correct and that our relationship is linear. And that means that the force between those two masses would have been equal to whatever the slope is divided by d squared. Well, every time we changed the mass, we got a different slope. And every time we changed the mass, we made the product of the mass half. So, and every time the slope was half as much. So once we graphed the slopes of the force over d squared graph versus the product of the masses, m1 times m2, we got a nice straight line again. So that told me that the slope was dependent, directly dependent on the masses, the product of the masses. So this tells me that the slopes would be equal to, now this slope should have been like 6.67 times 10 to the negative 11. And I'm just going to pick the letter G, capital G, to mean that, because I don't want to write slope again, because if I write slope again, then it's two slopes in the same sentence, and it's confusing. So I'm just going to call it a capital G, because I haven't used a capital G. Why not? So the slopes would be equal to G times M1, M2. Well, if I take this value right here and substitute it back in, I'm going to scroll up, substitute it back in right here, then I will get that the mutual force between the two objects, or their gravitational force, was G M1 M2 over d squared. And that is the gravitational force equation. All right, so first of all, let's define all these bits and pieces. So this is the gravitational force between those two objects. It depended on the mass. So this is the gravitational force. What's force measured in? Newtons, very good. And these are the two masses. And this is the distance from center of mass to center of mass. Remember in our simulation here, we were using the center of mass to the center of mass, like that. Okay, so the center of mass to the center of mass. Center of mass, COM, COM. And that should be measured in meters, and then it will be squared. And masses should be measured in kilograms, and then they would also be squared. And this is our gravitational constant, G. The Newton's gravitational constant, or the universal gravitation constant, 6.67 times 10 to the negative 11. And what would the unit be? What would the unit be? Let's do a unit check out here to the side. So when you're going to do a unit check, you can write, all right, so newtons would be equal to whatever our G is. We would have kilograms times kilograms, which is kilograms squared over distance, which would be in meters squared. So if you solve for g in little quotes, what would it be? G is going to be in Now, could you substitute in for the newtons? Yeah? So if you did that, your newtons would be, remember newtons were like kilogram meters per second squared because it was mass times acceleration. And then times meters squared and then divided by kilograms squared. And a kilogram will cancel, and then you'd have like meters cubed per kilogram second squared. Either's fine. You may see this way. This is what I usually write because it's, I don't know, it's easier for me to remember. That's pretty much it. And that's also correct. So don't let it throw you off if it's in SI units versus like some combined units. Newtons is actually like a compound unit. All right, so let's see how this matters. Like, what's the big deal about this gravitational force? Well, what do we call the gravitational force on you right now? Starts with a W, ends with an 8. Weight. Very good. And how do you calculate weight? That's right. M times little g, our gravitational field constant. Okay, so this is the mass of the object, and it's in kilograms. And this is the gravitational field constant for that planet, and it would be in meters per second squared. You could also say that it's in newtons per kilogram. I like newtons per kilogram when I'm thinking of it in terms of it creating a force and that sort of thing. So, what's different? So here's the Earth. And here you are, up here visiting Santa Claus. Are you a mass? Yeah. Is the Earth a mass? Yes. Are your center of mass separated? Yeah. The center of mass of the Earth is like way down here inside this doohickey, right here. And there is yours, okay? And Newton's third law says for every force there's an equal and opposite force between two bodies. So if the Earth pulls on you, what do you do to the Earth? You pull back. Okay, pulls. Okay, if the Earth's pulling on you, then you pull on it. If I push on you, you push on me. So it was kind of the same action word each time. So that means that the gravitational force between me and the Earth would be like capital G, the constant, times M1, maybe the mass of the Earth, times M2, maybe that's my mass, divided by the distance our centers are away from each other squared. But that's equal to mg, the mass of me times the gravitational field constant. So what's the gravitational field constant of the planet? You can divide by a little m on both sides and get that the gravitational field constant, or the gravitational field at any location. So if you wanted to find the gravitational field on the planet Earth, what would you use for R? So here's the Earth. What would you use for R if you wanted to find the gravitational field on the Earth? There's the center of the Earth. R is the distance from the center of the Earth. So we can calculate the gravitational field of any planet, any body, okay? We can calculate the gravitational field of a golf ball. What would we need to do to the golf ball? We would need to figure out the radius. How would you do that? With a ruler? You just hold it up and look at the ruler? Nope, can't cut it. How would you find the circumference? Okay. And use the circumference equation, 2 pi r. Okay, and then what else? All right, so we got the radius then, r. What else would we need to find? The mass. Very good. So, so this would be the mass of the thing, and this is the distance above the thing. From center of mass to the place. What do you mean, the place? Well, what if I wanted to find the gravitational field out here where a satellite may be orbiting? Boop, boop. Right? Is that the radius of the Earth? No, it would be some height above the surface of the Earth plus the radius of the Earth. So that is your R. Okay, so how are we going to find the mass of Mars? The mass of Jupiter? How do we know the masses of the... how can we even figure out the mass of the Earth? That's crazy, isn't it? Or the mass of the sun? So in order to find the gravitational field, we need the mass. Well, let's see. What can astronomers watch? We can watch the stars. What else can we watch? All right, so there's a planet, and we want to find its mass. We can watch how it moves, sure. What else can we watch? Jupiter has lots of them. Moons. We can watch their moon. So here's a moon. Okay? And what's that moon going to do? We'll pretend like we're looking down on it. We can watch that moon go. Oh, and this moon is awesome. It's moving in nearly perfect circle. Like we can't tell that it's not a perfect circle with our measuring instruments. So it's almost in a perfect circle. So what do we call the distance around the path? The path that the moon would take? The circumference. And how do we calculate circumference then? 2 pi r? Okay. And so the moon is moving, and it just, remember circular motion? V. So what's the definition of speed or velocity? Okay, and so that's the units, meters per second. So what did you have to divide by what to get meters per second? Distance over time. So if the moon goes around, then what's my distance? The circumference, 2 pi r. And the time for it to go around one time, it has a special name. The period. Okay. And do you remember this equation? I was like, it's essential for your success. So important, right? Okay. What keeps that moon orbiting that planet? Why doesn't it fly off? Yeah, there's a gravitational force. Isn't the planet pulling on the moon? F sub g. And the moon is also pulling on the planet. But right now I'm looking at what the moon does, because I can watch the moons go around the planets. So, let's see. That means that our gravitational force is pointing towards where? And what kind of force points towards the center? Or what do we call a force? Centripetal. So the gravitational force is centripetal. Your gravitational force, that's G, mass of the planet, mass of the moon, over R squared would be equal to mass of the moon. What was AC? The center-seeking acceleration, which was V squared over R. Does that ring a bell? Yep. So v squared over r there. What does it matter? The mass of what? The mass of the moon. Or the satellite, or whatever we have deployed into the atmosphere or surrounding the planet. What else can I do here? Can I multiply by r on both sides? Okay, so let's see. What have we got now? Spastic. Okay, here we go. So then the orbital speed would be the square root. I'm taking the square root of both sides because v is squared. Gm over r. So if I could figure out the orbital speed of the of the moon that I'm watching, I could probably find the mass. I'd have to like measure the radius of the orbit there. But this is the orbital speed of the satellite, or whatever it is that's orbiting. We can call everything that orbits a satellite because that's the definition. But so this is the orbital speed. But we can also call it tangential speed. And tangential speed is in meters per second. G stands for the gravitational constant. Capital M is the mass of the thing in the middle. So that's like the planet that's in the middle. If you're looking at a satellite or a moon that's orbiting. It could be the sun if you're looking at the Earth orbiting the sun. And R is the orbital radius. So from the center of mass to center of mass. Center of mass to center of mass. It's really important. Okay, so maybe I can watch some moons orbit a planet and figure out their orbital speed. But if I'm going to figure out their orbital speed, I'm probably going to have to like watch their path, figure out the radius, use the period, because the period is, or the orbital speed would be also 2 pi r over period. So what if I just combine those two? If the orbital speed or a tangential speed is 2 pi r over period, and an orbital speed for a satellite is gm over r, can I just set those equal to each other? What do you think? Yeah. So how about let's set 2 pi r equal over period equal to the square root of gm over r. So let's solve. So what's something that would be pretty easy for an astronomer to measure if they're watching a moon go around a planet? The circumference or the radius, right? We can look at it and see how far it is and use some geometry to figure out the circumference. What is the other thing that you can sit there and watch and you got your stopwatch going on? The period. So let's solve for the period here. If I solve for the period, I need to square both sides. Actually, let's go back a step here. So 4 pi squared r squared over period squared would be equal to gm over r. Right, squaring both sides. So then 4 pi squared r cubed divided by gm would be equal to period squared. Take the square root of both sides, put period first. The period will be the square root of 4 pi squared r cubed over gm. So can an astronomer determine the mass of the thing in the middle by watching and observing the moon orbit the thing in the middle? This is the mass of the thing in the middle. Maybe that's the sun. I mean, like, we've timed the period of the Earth going around the sun. This is the orbital radius. So R stands for the orbital radius measured in meters. The t is the period of the satellite, the thing that's doing the orbiting, and period in this equation is measured in seconds. So one thing we need to be careful about is that, like for example, what's the period of the Earth's revolution around the sun? About the sun, it would be 1 year, which is what, 365.25 days. And then you'd have to finally get it to seconds, which is a lot of numbers. It's in that Rent song, right? So what happens when we have multiple forces? Multiple forces acting on the same body. Okay, so when we have multiple masses, then our object just is in the middle of a tug of war, okay? So let's say we have the sun, and the sun is freaking huge, right? And you've got the Earth over here, not drawn to scale, and here's the moon, right? Now, the Earth is being pulled on by the sun. FG sun. And it's being pulled on by the moon. FG moon. So if you wanted to find the net force on the Earth, what would you have to do? That's my little free body diagram. You'd have to sum those forces, right? Yeah, you'd have the FG moon in this frame of reference minus FG sun. And that would be the total sum of the forces acting on the Earth. Now, what about sometimes the sun, is over here, and the moon is right here. And then when the Earth is right here, okay, what's the moon doing to the Earth? It's pulling on it. What's the sun doing to the Earth? It's also pulling on it. Do you know what happens when the moon and the sun all line up on the Earth? Well, we can get an eclipse, that's right. But when you're at the ocean, what happens at the ocean? We have tides, right? High tide, low tide, and it depends on the position of the moon. And when you've got them lined up with the sun, then it's going to be even higher tides than normal. It doesn't happen all the time. But the tides kind of follow the moon because there's a gravitational pull, and the water is fluid and it can bulge, so to speak. So when you have this lined up like that, so what's going to happen? There's going to be tugged one way. So maybe when the Earth is between the moon and the sun, maybe it's tugged towards the sun or towards the moon. Sorry, because the moon's way closer. So it's tugged towards the moon, and then later when the moon and the sun are on the same side, the Earth will be tugged towards the sun. So what does the Earth do just a little bit as it goes around in its path around the sun? It kind of wobbles just a little bit. And there's all those little bitty things that make a big difference. Also, the axis of the Earth precesses over time as it goes around. There's like a wobble. So we're actually orbiting kind of like this around the sun. Kind of cool.